Hey guys, Miss Peterson here. And today, what we got going on is a fluids FRQ problem. This one is from the 2017 released exam, and it is number 1 on that exam. So what we have here is a pipe. It's probably a little hint. This one's going to have to do with Bernoulli's a bit. And it says 2 students are observing water flowing from left to right through a section of the pipe shown above. Okay, so we got the fluid flow in that direction. Which decreases in diameter and increases in elevation. The pipe ends on the right where the water exits vertically. At point A, the water is known to have a speed of 0.5 meters per second and a pressure of 2 times 10 to the 5th pascals. The density of water is 1,000 kilograms per meters cubed. Okay, here we go. So we have this pipe. It is flowing. It's going upwards. One of the things I do like to do when starting these types of problems is write out my list of variables. So I'm actually just going to type those up right here. Starting with at point A. At point A, we can actually find the area of the pipe. You might know that that's a thing we're probably going to need. If you look, they're talking about the speed in part A, but we are going to have to do some calculations. So I find it easier to just calculate some of those things right away. Okay, so at point A, the radius of the pipe is 1/2 of that 2.5 centimeters. So that's 1.25 centimeters, which is 0.0125 meters. So the area then will be pi times r squared. So when you plug that into your calculator with that r right above there, so 0.125 squared times pi, we get 4.9 times 10 to the negative 4th meters squared. 4.9 times 10 to the negative 4th. Oops. There we go. Meters squared. Okay. And then what else do we know at point A? The speed of it is 0.50 meters per second, and its pressure is 2.0 times 10 to the 5th pascals. Okay, we can do the same for point B. Okay, point B has a radius of 1.5 or half of 1.5 centimeter. So that's going to be 0.075 centimeters. Okay, right? Just 1.5 divided by 2, 0.75 centimeters. Oops, one too many decimal places there. 0.75 centimeters, which will be 0.0075 meters. We can then calculate the area. Pi times r squared. So when you plug that into your calculator, you get 1.76, so I'm going to say 1.8 times 10 to the negative 4th. Times 10 to the negative 4th meters squared. And then we know that if we ever have to do its height, we would say that the height at point B, we would probably set the middle of A as our 0, so at point B it would be at 5 meters. Okay, and then we might need the depths and stuff, but that's some of the information given to us in the problem that might be, that might be helpful for us later on. Okay, so let's go ahead and get started. The students disagree about the water pressure and speed at point B. They make the following claims. Student Y claims that the pressure at point B is going to be greater than at point A because the water is moving faster at point B. Okay, let's go ahead and look at that. So we do know that at point B it'll be moving faster. We know that because of the continuity principle, which is that the flow rates need to be equal. So the volume times the speed, area times the speed, at each of those points needs to be equal. Since this one has a bigger area, B is going to have a faster speed. So that part of his claim is true, but that doesn't mean that the pressure's going to be lower. Okay, Now, student Z claims that the speed of the water is less at point B than at point A because by conservation of energy, some of the water's kinetic energy has been converted to potential energy of the Earth water system. And what all these bullet points are is they're asking us to analyze those claims, analyze them for things that they said that are correct and for things that they said that are incorrect. So to make that a little bit more organized for us in this video, I made a little chart. Okay. So for student Y, the correct parts of their claim is that the water will be moving faster at point B, okay? They claimed that the water's moving faster at point B. That is true. But the incorrect part is the pressure, okay? The pressure at point B will be lower than the pressure. Or no, the incorrect part of his claim was that the pressure at point B will be greater than at point A. Okay, that was an incorrect part of his claim. Now, for those ones, it does want us to justify it. So we will say the pressure will be lower, okay? But why is it lower? That is due to Bernoulli's principle, okay? And because of the speed thing. So first, let's go ahead and talk about the speed. Because of the continuity equation, that is the A1V1 equals A2V2, okay? We know the speed at point B will be greater. In addition, point B is at a higher elevation. So it will have, it's at a higher elevation. Now, both of those are terms in Bernoulli's equation. So if you guys remember Bernoulli's equation, so it is P1 plus rho GY1 plus rho V squared. Shoot, why don't I remember Bernoulli's equation? You know what? We're just going to go grab it from the equation sheet. That is always a good call. Okay, so let me go ahead and just go over to my equation sheet. Okay, so there's Bernoulli's equation as it is on the equation sheet. So if this is at point A and this is at point B, we know these have to be equal. But both this term and this term in Bernoulli's equation will be higher at point B. It's going to be at a higher height and going at a faster speed. So that means this term must be drastically lower. Okay, so let's go ahead and explain that thoroughly. Looking at Bernoulli's principle, if the elevation and the speed increase, the pressure will decrease due to conservation of energy. Okay, Bernoulli's principle is basically a statement of the conservation of energy in a fluid. This one is like the potential energy term, this is the kinetic energy like term, and then this is the pressure energy. Okay, cool? Okay, cool. Now let's look at student Z's claim. Student Z claims that the speed of the water is less at point B than at point A. Well, that's incorrect. Okay, the speed let's go ahead and put those in quotes so we know that that's the part of the claim we're talking about. So he said the speed of the water is lower at point B. Okay, now that is incorrect. Okay, that is just not a true story for this. And we already explained that in this part of our answer. But then he said, but by conservation of energy, some of the water's kinetic energy has been converted to potential energy of the Earth's water system. Now, it is true that it did go up in potential energy. So that is a correct part of his claim. You could also claim none here and still get full points on the scoring guidelines, but it is true that the potential energy of the water in the pipe increases in that Earth water system. So that is one correct part of it. Okay, but the speed of it being lower at point B than at point A is not correct. And I don't know if it's the kinetic energy that got converted. Okay, so first let's go ahead and explain the continuity. Okay, because of the continuity equation, we know the speed will be higher at that point B. Why is it doing that? Come on. Sorry, guys. There we go. Okay, so we know that the speed at point B will be greater. Okay. So that is that. Some of the water's kinetic energy is converted. We do know that energy is conserved. That is another thing that we could say is correct. But we don't really know if it's the kinetic energy that gets converted, because the kinetic energy is also increasing. Both the kinetic energy and the potential energy of the water are increasing. So the energy is not being converted from kinetic to potential. Rather, by Bernoulli's principle, as shown above, the pressure of the water will decrease. Okay, and that's how we can kind of apply Bernoulli's principle conceptually to evaluate those claims. Okay, cool. Okay, cool. Now we're going to go ahead and calculate the following at point B, the speed of the water and the pressure in the pipe. So let's go ahead and start with the speed of the water. Okay, so that relies on our continuity equation. A1, V1 was the area of A, velocity at A equals the area at B times the velocity at B. So if we're looking then for the velocity at point B, it's going to be the area at A times the velocity at A divided by the area at B. And remember, we had already calculated these numbers back at the start of the problem. I'm going to go ahead and change my marker color and write in green for that. So the area is 4.9 times 10 to the fourth, and the velocity is 0.5. Okay, so we have 4.9 times 10 to the fourth meters squared times the speed, 0.50 meters, divided by the area at point B, which is 1.8 times 10 to the negative fourth. I forgot the negative there. 1.8 times 10 to the negative fourth meters squared. Okay, so, oops, and this is meters per second, because then the meters squared and the meters squared cancel out, and we're left with meters per second units. So we plug that into our calculator. And we get 1.36 meters per second. Okay. Okay, so if we round that, I would just say 1.4 meters per second is the velocity at B. Now, if we want to calculate the pressure in the pipe at point B, we're going to need to use Bernoulli's equation. So let me go ahead and write out Bernoulli's equation again. Oops, I didn't need to highlight anything. I'll just use blue. So for the pressure in the pipe, we start with Bernoulli's. P, pressure at A, plus rho G height A, plus 1/2 rho V squared. I do not know why it's highlighting this. Equals the pressure at B plus rho G Y B plus 1/2 rho the velocity at B squared. Okay, so we can eliminate some of these terms. We know that the height at point A, we can define that as our 0 line. So then our height at B is going to be 5. And if we get rid of the height at A, we count that as 0, then we can ignore that term. Okay, and again, we're trying to solve for the pressure, that term right there. So it might be a little bit easier to reorganize this equation and solve it out. So we have that we're going to move both of these terms over to that side, subtract them from both sides. So then we end up with the pressure at B equals the pressure at A plus 1/2 rho velocity at A squared minus rho G Y B. Why did I do that? YB minus 1/2 rho times the velocity at B squared. Okay. We could factor out some things, try to make that a little easier. Let's go ahead and do that. Actually, I don't think it's going to make it that much easier for us. I think it might be easiest to just go ahead and plug in the numbers. So, that's what I'm going to do. So, we have, okay, the pressure at B equals the pressure at A. What? I don't even know what it's doing with the highlighter. It is being funky today. Sorry, guys. So we have the pressure at A, 2 times 10 to the 5th. Stay. No. Stay. Okay, so we have 2 times 10 to the 5th pascals plus 1/2 times the density of the water, 1,000 kilograms per meter cubed, times the velocity at A, which we have written in the previous problem, 0.5 meters per second. Okay, minus the density of water again, 1,000 kilograms per meter cubed times gravity, 9.8 meters per second, times the height at B, which was 5 meters. And one last term, minus 1/2 times 1,000 times the velocity at point B, which we just calculated as 1.4 meters per second squared. A lot of terms going on there, but let's go ahead and see if we can do this. To make it a little bit easier for you guys to see, I am going to go ahead and calculate them all individually and then do it all together. So we have 2 times 10 to the 5th, nothing we can do there. But then we have 1/2 times 1,000 times 0.5. Okay, that number is Okay, that number is 2.5 times 10 to the second. Okay, and then we have minus the next term, which is 1,000 times 9.8 times 5. Okay, 4.9 times 10 to the fourth. Okay, minus 0.5 times 1,000 times 1.4 squared, which is 9.8 times 10 to the second. Okay, remember to square the 1.4? Yes, okay. So then we add and subtract all those terms together. And we get 1.5 times 10 to the fifth, okay, which is correct indeed. The pressure at point B is 1.5 times 10 to the fifth pascals. Okay, cool. Okay, cool. Yay for using Bernoulli's. A lot of math there. Easy to make a little math mistake, so really make sure to show your work on that AP exam. Okay, the valve to the left of point A now closes off that end of the pipe. The section of the pipe shown is still full of water, but the water is no longer flowing. Okay, so now we have a static fluid, and it's asking us to calculate the absolute pressure at point A, the pressure that includes the effect of the atmosphere. So the pressure at A is going to be equal to atmospheric pressure plus rho g y. I think it might be rho gh on the thing, but that is the height component. Now, for that height component, we have to take into consideration the total depth, okay? And that total depth is going to be 6.0 meters. Now, it doesn't tell us what the atmospheric pressure is, but it's actually on your equation sheet. It is 101 kilopascals. So 1.01 times 10 to the fifth pascals. So 1.01 times 10 to the fifth pascals, I think that's how it is on your equation sheet, plus 1,000 times G, 9.8, times the height, the depth, which is 6 meters. Okay, I think it is H on here because it is the depth to kind of get it different from that Y term in Bernoulli's. So let's go ahead and plug that into our calculators. 1.01 times 10 to the fifth plus 1,000 times 9.8 times 6.0, and you get 1.59 times 10 to the fifth, which we would probably just round and say 1.6 times 10 to the fifth pascals as the pressure at point A. Okay. Now, an air bubble forms at point A, where the dot represents the air bubble. Draw a free body diagram showing and labeling the forces exerted on the bubble. Draw relative lengths of all vectors to reflect the magnitude of forces. Okay, well, picture. You got a bubble in water. What way is it going to go? Up. What force is responsible for it going up? Well, that's the buoyant force. So the upward arrow is going to be the buoyant force. Okay, FB equals buoyant force. And then even though it's air and the buoyant force is going to be bigger, there is a force of gravity on the bubble as well. So we have gravity and the buoyant force. Okay, cool. Okay, cool.